How do I get into this situation? Well, it's like I'm trying my acid. Oh, an 18. Oh, strawberry. No. Where's the go?
The people who live in the house are supposed to have like a little gathering, supposed to relax and.
Every time it gets
That's
on the
supposed to be our,
it's
it's
like,
like how it's six.
I can smell
Really
it.
don't know
It's
what's
brown.
happening. Literally, it's gonna be. Raise your hand, North Carolina on. And get there. We don't do
All right, good morning, everybody.
Good morning.
Today we're going to get into chapter 21, which is talking about phenols and aerial halides. It's not a terribly long chapter, so that's good. So for Friday, we'll have an inverted lecture over chapter 21, but we'll also, I want you to read special topic G in the book, which is on some carbon-carbon bond forming reactions that are fairly popular today. They're more modern type reactions that have resulted actually in a Nobel Prize. So read special topic G, it's not too many pages in length. So we all know what a phenol is, right? It's a benzene ring with an OH group attached to it. And so you might argue that it's an alcohol, but in fact, phenol is a special functional group. Why is that? Why do we not consider this just a typical alcohol? It's on a benzene ring. But what does it do that makes it different? What is that benzene ring? What property is different from a phenol than an alcohol? There's a lot of things that are similar, I'll give you that. But what's different between a phenol and an alcohol? It is stable. What else? Pardon? It's aromatic. What else? How about that OH? Is it the typical pKa of an alcohol? Is it more acidic or is it less acidic? Delicious. Pardon? Did somebody say? You didn't say? Thought I heard it.
More acidic.
It's more acidic. That's right. Why is it more acidic? It's more acidic because the conjugate base is more stable than an alkoxide, right? Because we can draw resonance structures. What's the approximate pKa range for phenol? It's about 10, yeah. So the pKa is around 10 for a typical phenol. Where is it for a typical alcohol? About 16 to 18, somewhere in that range, depending on what the R group is, right? So big differences in acidity, right? And so that really dominates the chemistry of the phenol. So we can synthesize phenols through a variety of processes. We learned last night that you can take aniline and you can convert it to a phenol pretty readily. If you convert the NH2 into a diazo compound, so we would treat this with HCl and sodium nitrite, which would give us the diazo compound, and then we would boil it up in water and maybe add a little copper oxide to catalyze the reaction, and we can form the phenol quite readily. Okay? That is one way in which we can make phenols, but there are many, many other ways to make phenols, and we're going to talk about those today. Another classic way of making phenols is through a process known as the Dow process. Anybody know where the name comes from? Dow Chemical. This was the Dow Chemical process that they used many years ago. And they started off with aerial halides, in their case chlorobenzene, and they were able to convert that into phenol in one pot, essentially, using sodium hydroxide in excess, water, and high pressure, and about 350 degrees Celsius. So they would really increase the pressure of the system so that water wouldn't boil at 100, and they heated it up to 350 degrees Celsius. And after workup, which they dump it into acid, they get the phenol. Okay? This process is no longer readily used. Can anybody tell me why?
They have a better one now?
They do, but why not stick with what worked? What's wrong with this process? Why would a company be seeking a better route to it than this?
It's cheaper, isn't it? The new route's cheaper.
Okay, so what's so expensive about this route?
Excess sodium
Hydroxide's pretty cheap.
You have to get it at a high pressure.
High pressure and high temperature. It requires expensive equipment, requires a lot of energy. Phenol is a commodity compound. What do we know about commodities?
They fluctuate a lot.
They fluctuate in price, and none of them are terribly expensive. Okay? That's what a commodity is. Okay? So you don't want to generate a commodity through an expensive process. Okay? And so the Dow process has been replaced. The mechanism for this we'll talk about on Friday. It's an interesting mechanism. It's not what you think. It goes through what's known as a benzyne intermediate. Benzene with a triple bond in it, actually, which doesn't sound very stable, right? And in fact, it's not. And so, but we know that that's the mechanism for this particular reaction, because sodium hydroxide can't function as a nucleophile on an SN2 hybridized carbon. I mean, it can't get from the back and push out the chlorine, so we know that that doesn't happen. The way that we currently make phenol industrially is through the cumene hydroperoxide process. So you start off with cumene, which is readily available from benzene using electrophilic aromatic substitution. So you take propene and benzene and an acid catalyst, and you can get cumene very, very easily through EAS. And what they do is they take this and they expose it to oxygen and heat it up a little bit, not to 350 degrees. And then they treat it with dilute acid. And what you get out of this is phenol and acetone. Both products are commercially viable. Acetone is paint thinner, fingernail polish remover, organic solvent, whatever you want to call it. It can be sold. And phenol has a variety of uses. So the products that they get out of this are readily sellable, if you will. Also, if you look at the reagents, what can you tell me about the reagents as opposed to the Dow process?
Pretty easy to get your hands on.
Pretty easy to get your hands on. Oxygen, all they do is bubble air through the solution. Okay? And so this actually, the mechanism for this is pretty interesting. If we're using oxygen, what kind of mechanism do you think it is? It's a free radical process, that's right. And in fact, if you ever find an old bottle of cumene in a laboratory that's been around for a few years, it oxidizes quite readily in the air through a free radical process to give cumene hydroperoxide. That happens just sitting on the shelf. In fact, when I was a postdoc, we had an old bottle of cumene. It was labeled as cumene, actually, sitting around. It was about, I don't know, probably 500, 600 milliliters of the stuff. And an undergraduate student was doing some work with cumene hydroperoxide, and he got the smart idea that he would just extract that old bottle and get the cumene hydroperoxide out of it without having to buy new stuff. And in fact, out of that 5 or 600 milliliters of material, he got about 40 to 60 grams of cumene hydroperoxide out of it. And it had just sat there for years. And so he was able to get this quite readily. Are the oxygens where we need them? What carbon are they on? Pardon? The benzyl carbon, that's exactly right. Now we need one oxygen on the benzyl carbon. because that's what's going to make acetone, right? But where do we need the other oxygen? We need the other oxygen to be on the benzene ring, right? So how do we get that there? What kind of reaction do you think is going to happen when we take this and expose it to acid?
Acid base.
We are going to have an acid-base reaction, but we're also going to have a rearrangement. We've got to rearrange some bonds here. And it turns out that under the acidic conditions, this terminal oxygen gets protonated. Now what do you think happens?
The leaving group leaves.
The leaving group leaves.
OH2 positive. Is that right?
It's a pretty good leaving group, right? Yep. You're on the right track. But if it just leaves, I end up with an oxygen with a positive charge. You think that's a good thing? So I said a rearrangement has to occur, right? So what happens is we have a shift. You remember in carbocations we could get alkyl shifts? In these hydroperoxides that are protonated, you can also get shifts of carbon-containing groups. And it turns out that the aromatic ring shifts, attacks the oxygen, and water leaves as a leaving group. And so that gives you the benzene ring oxygen bond that you need. Now what happens? If I have a carbocation and I got water around, what do you think is going to happen? Yeah, water's a pretty good nucleophile with a carbocation, right? And ultimately what we get is that. What is that? What's that functional group we just created?
Ether and alcohol.
Part of it looks like an ether, part of it looks like an alcohol. But when the alcohol and the ether share the same carbon, we talked about this functional group. What is it? Close. Hemiacetal. That's right. It's almost like a sugar, right? So we generate a hemiacetal. And what do we know about hemiacetals? In the presence of water, and acid, they fall apart into ketones and alcohols, which is, in this case, a phenol. So I'm not going to go through that mechanism. But this is a lot simpler process than using the Dow process. You end up with two products that are commercially viable. They both have a market. You don't have to use a whole lot of energy. Of course, you do have to boil the cumene up in the presence of oxygen, but that's not a big problem. And then you just use dilute acid, and you can get your phenol quite easily. So what are some of the uses for phenols? Pardon?
Where do you use them in medicine?
They are used in medicine. So they do have use in medicine. They have use as antioxidants. Remember, vitamin E is a phenolic containing molecule. And when we talked about free radical chemistry in chapter 10, we talked about antioxidants, and they were phenols. BHT was a synthetic version of vitamin E in a way. So they're used as preservatives, as antioxidants. You'll find them in many of your cosmetics to provide you with that antioxidant, anti-aging kind of stuff that they always talk about. They're also useful in the Williamson ether synthesis. And they're useful in the formation of carbon-carbon bonds, which we'll talk about today as well. Okay? Why would a phenol be more useful in the Williamson ether synthesis than an alcohol?
Stabilizes. Benzene's still stable whenever you lose the oxygen.
We're not going to lose the oxygen, though,
Oh, for ethers.
for the Williamson ether synthesis. What is the Williamson ether synthesis? Refresh my memory. What is the Williamson ether synthesis? What do you think, Maggie? What are we going to make in a Williamson ether synthesis? Let's start with what we're going to make. What's the functional group we're going to create?
Ether.
Ether. It's in the name, right? Now, what was the Williamson ether synthesis? The Williamson ether synthesis, remember, was an alkoxide plus an alkyl halide to give an ether. And it was an SN2 process. But a typical alcohol that we would use to make the alkoxide has a fairly high pKa, right? 16 to 18, depending on what the R group is. Maybe even a little higher. But what about the phenol? What did you say earlier, Matthew?
It was around 10.
It's around 10, so it's a lot easier to do what?
Acid-base chemistry.
It's a lot easier to do the acid-base chemistry. And in fact, you can take phenol and take a very mild base like sodium hydroxide, and you can deprotonate it readily to give what we call the phenoxide. And of course, the sodium counterion is around. And that oxygen can actually function as a reasonably good nucleophile in the Williamson ether synthesis. And so you can react it with alkyl halides and you can make carbon-oxygen bonds, for example. Now, it turns out that I made this particular one because this particular ether is actually good at making a carbon-carbon bond through a rearrangement known as the Claisen rearrangement. Claisen, kind of, his name pops up quite a bit, right? And so the Claisen rearrangement, you would take this and you would heat it. And you would make that carbon-carbon bond. Okay? Take me through the mechanism of how that happens. Propose a mechanism for me. It's okay to be wrong.
Does it have something to do with lone pairs on oxygen?
It does have something to do with that.
The carbon group that you want attached to the oxygen has to somehow leave and go to another carbon somehow.
It does have to leave and go to it, that's right. You're heading down the right rabbit hole. Does it do what?
Just one of the lone pairs on oxygen. Alpha hydrogen.
Let me draw it a little differently here. that hydrogen in there for good measure. Now, somebody told me that it has something to do with the lone pairs on oxygen. What can I do with those lone pairs on oxygen? Attack the what?
The carbon connected to the hydrogen.
You think those lone pairs can reach that hydrogen? What can those lone pairs do?
Form a double bond.
Can form a double bond where?
From the ring and
Okay, so we can push these into the ring by resonance for sure, right? And so when we do this, I can't have 5 bonds to this carbon, right? So what happens to this double bond? What does it do? What's that? But where does it go? They don't just disappear into thin air, but it does go somewhere. Where does it go?
it's a carbon.
You can think of it as a carbanion, but I don't have to do it that way. That's not necessarily wrong. I could push those electrons onto this carbon. Or I could push these electrons to what carbon? That carbon, right? But I can't have 5 bonds to this carbon, so what happens?
It goes to the next one.
And so we end up with and now what happens? I just made the carbon-carbon bond, right, Gabby? So now what happens?
The lines go up from the O, go up to the minus, and then that attacks the hydrogen, and then one goes over.
Essentially, that's right. And we call this process what? Tautomerization. This is a ketone. This is an enol. That's what a phenol really is in a way, right? We have keto-enol tautomerization. And equilibrium lies to the enol form. Is that what we learned in the previous when we talked about enols?
No.
We said that the keto or the aldehyde form favored, but why in this case does the enol form more favorable than the keto form?
It's aromatic.
It's aromatic. That's exactly right. Phenols are the exception to enol stability because they're aromatic. It's another difference between alcohols and phenols. This is known as the Claisen rearrangement. This simple little reaction has actually been used both industrially and academically to make very, very important molecules. And the importance of it is, think about it, very simple formation of an ether through Williamson ether synthesis, 100% yield almost. Really good reaction. And then all I have to do is heat that up and I can form a new carbon-carbon bond. Right? So now you've learned many ways to make carbon-carbon bonds.
Can that be repeated multiple times since you have the alcohol or the phenol group still there?
Could you put another group on there and repeat? In theory, yes. I don't know that I've ever seen anybody do that in the literature, but I'm not saying it hasn't been done. But I mean, I could do it on paper for sure. Absolutely. Now, how do you think we know that this mechanism is concerted like this? What experiment would you go into the laboratory and perform to prove this? Or to disprove it?
Like to find the presence of a new double bond or something like that? Maybe carbon-carbon bond?
Do you do IR?
What would the IR tell me in terms of the mechanism? I mean, I can do IR on it,
Yeah, you should.
but what's it going to tell me? We're suggesting that this mechanism, that all the atoms in this ether are what end up in the product. But for a long time, there was actually a debate as to whether this group actually came off completely as a carbocation and then just did simple electrophilic aromatic substitution on a phenol. But they disproved that. how might we do an experiment to prove this mechanism over that mechanism where the allocation leaves? That's fairly stable, right? It's conceivable that the allocation could leave and then simply react with the aromatic ring in an electrophilic aromatic substitution reaction. That's a plausible mechanism. I would actually give you some points on an exam for that. It can be rationalized, but it's not what happens. How did they prove it? In the concerted mechanism, what carbon-carbon bond must be formed? It must be between this carbon, or this carbon, right? And that particular carbon of the ether, right? So what they did was they labeled this with carbon 14. What's carbon 14? It's radioactive. You could also label it with carbon 13, but in the traditional experiment they actually labeled it with carbon 14. Where, if this mechanism is true, where does the carbon 14 have to be in the product? It has to be the carbon that's part of the carbon-carbon bond, right? And that's all they saw. 100%. That carbon 14 was part of that carbon-carbon bond. They could tell it by a variety of techniques. If Matthew's mechanism is correct, and this leaves as the carbocation, I'm going to put a star there for carbon 14, right? Where would the carbon 14 then be in the product?
Still on the end.
It could form, it has a 50-50 probability of forming the carbon-carbon bond that we need, or being the terminal carbon, because this is a resonance stabilized carbocation. And the nucleophile could attack this with equal probability of attacking that. They did not see a 50-50 distribution of C14. So they know that this has to be this intermolecular concerted mechanism. Okay? Although on paper, you could rationalize the carbocation leaves because it's relatively stable, resonance stabilized, and then it undergoes another reaction. But that's not what's happening. It actually goes through this 6-member transition state to give the product that's shown. Okay? So these labeling experiments prove useful in determining these reaction mechanisms quite frequently. Other uses of phenols, the Kolb synthesis. And this is a really neat reaction because you take phenol, you take sodium hydroxide, and you put in it carbon dioxide, and we're going to form a new carbon-carbon bond. And what we get out of that particular reaction after workup is that simple little molecule. After workup, after we work it up with dilute acid. So first this, then dilute acid. What is this? Does anybody know what that molecule is? It comes from the bark of a willow tree. Does that help?
Get a second. Go on.
See you in a minute.
Use it to sentence.
Same kind of class of drug though. What's the original? Aspirin. That's salicylic acid, which is the precursor to aspirin, which is acetyl salicylic acid. Okay? And so this reaction is kind of neat in that you actually form the phenoxide because of the pKa, right? So you form the sodium phenoxide, and that reacts with the carbon dioxide. So we have the keto form, and we know it likes to form the what form? The enol form, so it tautomerizes, right? And after workup, we get the product. What's cool about that reaction, other than we're forming a precursor to a highly utilized drug? Does anybody know what aspirin's really used for these days, other than headaches?
Heart disease prevention?
Well, not heart disease prevention, but to help people from suffering a heart attack. Your heart can still be diseased, but it's there to help with people who've had a heart attack should be on a low-dose aspirin regimen. There's technically no such thing as a blood thinner. Your blood doesn't actually thin, but that's what we call it, okay? But aspirin is, so you take like what they call the baby aspirin. Does anybody know what the problems with aspirin are? It can cause bruising. It can cause ulcers. And it's actually this molecule right here that's responsible for the ulcers, the salicylic acid. But infants, you used to have St. Joseph's baby aspirin. It's hard to find now. Can anybody tell me why? Infants that took aspirin to relieve fever actually ended up becoming mentally challenged, is a way to put it. I mean, I forget the name of the disease right now, and I should know it because one of my cousins suffered from it. She was given a dose of aspirin as a young child, and then she was essentially non-functioning for the rest of her life. Trying to remember the name of that disease now. You can look it up, okay? But we almost have Down syndrome-like behaviors. And one day you're normal, the next day you're gone. I mean, in that regard. So it does have some issues. And so how do we get from salicylic acid to acetylsalicylic acid? How do we do that? What's the functional group that we're changing? We went from a phenol, not necessarily an alcohol, to an ester. So we're doing an esterification. How can we do that? Technically, you could use the Fischer esterification, but they don't. They do something a little easier than that. They actually react this with acetic anhydride. It's basically a mild form of acetyl chloride, and it puts the acetyl group on to give you the acetyl salicylic acid. Why do we acetylate salicylic acid to make aspirin when we know that the pharmacologically relevant drug is the salicylic